So this is going to be the first lesson for stats. It's kind of like the lesson 0.1. It's not quite chapter 1. It's just kind of going over a few um, basic things here. If my mic cuts out in the middle, I'm going to turn it back on. So if you hear me pause or just cut out suddenly, excuse me, just give me a moment and I'll turn it back on. It should only happen once, if at all, but just a fair warning. So we're just going to basically review sort of the idea of bad statistics, which kind of sounds counterintuitive, right? Why would we go over what bad statistics are? But this is so that we can avoid these very common and easy to think of mistakes. So we're just going to be kind of looking at a few examples of some statistics that people assume are kind of nice and truthful, but can easily be misleading. So just going to kind of start off kind of light in this section here. So first off, we're going to go over the concept of validity, which is very important in stats. We want to make sure our stuff is valid. And it's basically it's not necessarily a yes or no kind of question. Validity is the degree, as it says here, the degree to which the evidence supports the interpretation. So there's a few things you can kind of ask yourself here to kind of test the validity of what something is. So was the correct question asked? Was the correct analysis used? Was the conclusion fitting with the findings? That sort of thing here. But validity is not necessarily a yes or no thing. You can have two things that are valid, but one thing be more valid than the other. Because again, stats is not about figuring out 100% certainty. Stats is about giving the most accurate information about a situation. And that very often is not necessarily going to be, I know this is going to happen 100% of the time. There's an old joke that, being a statistician means never having to say that you're certain, because we don't deal with certainty. We deal with degrees of possibilities at most. So validity, again, is not necessarily a yes or no type thing. So we're going to talk about how we can mislead with statistics here. Again, just to make sure that we avoid these very common, easy, unthoughtful pitfalls. So these are things that you can step into without even knowing them, so you have to make sure that you're on your toes about it. So first off, we have a very easy concept of biased or bad sampling. So this is unfortunate because it does not show what I want to show, so let me try something here and go back to this. There we go. So this is what I wanted to show here. So this is a report. It says the time. This is called the New York Times, by the way. This is not something else. So the New York Times leaves behind the rest in print and online. So this is kind of showing the visitors to the Times websites and the sale price of the Times versus the Daily Telegraph and all that. But again, this is the source here. It says source ABC, January. And then here we have the source, which is kind of blurry to read, but we don't know yet. But what you want to be careful of here is who is reporting this. Well, if this was an ad or a section of the Times newspaper, if the Times itself was reporting this, then a red flag goes up saying, okay, well, they're reporting this. That means they're probably going to cherry pick data or studies or surveys that fit their description, their desires there. So you have to be kind of careful of, again, bias here. Or if the Times itself kind of made these surveys, so let's say the Times was reporting their own data, well, did they actually get people from a statistically sound method there? Did they pick people from a variety of locations? Did they just kind of use people that called in after they put out a want ad or something like that? So again, if they sampled people that were already predisposed to reading the Times versus something else like the Daily Telegraph, then that's going to skew their data. So if you get a bad sampling or a biased sampling, your data, no matter what you do to it, is always going to be skewed towards that bias. So if you pick from an area where the Times is very popular and you say, hey, everybody likes this magazine or everybody likes this newspaper because this study shows that, well, yeah, the study shows that because you picked people from an area that mainly read that newspaper rather than people from an area that might have a little bit different point of view or something like that. So again, bias sampling is a very big and easy mistake to make in stats. So you always want to make sure that your sampling is representative of the population you're assessing. So if you're trying to get people's opinion on the Times in New York, you want to make sure you gather data from everybody all around New York, not just in one location that the Times might be popular in versus, again, a variety of locations. So always question kind of where the sampling is coming from in order to best get the answer there. Lying with charts. I can go back to my big screen here. Let's try that. And here we go. So uh, sometimes people get a little bit too creative in how they want to represent an concept. So this is about fuel economy. So obviously the graphic designers here or the stats designers here wanted to make this look like a road, like someone was traveling down a road to kind of help present their data. And having a good sort of artistic flair to your graphs is not necessarily a bad thing. It keeps people interested. It can help prove your point. But if you're going to be representing something with stats here, you want to maintain consistency. So if you look here, these numbers are not evenly spaced. They get closer and closer and closer together as you go up the ladder there. And on this side too, they get closer and closer and closer together. So that's what we call a distortion, which means that you're not really representing the actual change of what you want to try to do here as you go down the graph there. You want to maintain some sort of consistency so that people can get the idea of what's happening and how big a shift there is in relation to each other. Because even though these numbers, 27, 27 and a half, they're pretty close together in the number line, but they're really far apart here. Whereas 19 and 20, they're further apart on the number line than these two, but they're much closer together up here. So they're not really representative of where they actually are on a true number line. So again, it's just because they're trying to be a little bit too creative here that their graph is kind of distorted and the data is not necessarily going to be representing what they want to do all that clearly because of the way they tried to put their artistic flair on this graph here. So be creative in how you present stuff, but also make sure that's still logically sound and easy to interpret here. Don't get lost in your artistic flair, so to speak. Because again, you want to make sure that numbers are represented well. So if numbers are closer together on the number line than they appear on the graph, that's an issue. Come on. There we go. So again, this is another case where people are trying to take a creative approach and they get lost with it essentially. So they have a chart down here that represents their yearly, looks like prices or sales. So it represents the yearly dollars per barrel. I don't know why it's going off the edge there. Whereas in this graph here, I'm not sure again why there's that sudden line there, but this graph here represents the quarterly sales, which again, it's kind of a weird thing to do because is this quarterly just for this year here, which it looks like it's 1979, or is this again quarterly for some other year in here or something like that? It's again, it looks like it's 1979, but it looks like from this point of view, if people didn't see this down here, they might assume that they're zooming in on the 78 bar here, because that's what my first interpretation was when I first saw this was, okay, this is the quarterly for the 1978 year, but down here it says 1979. So again, it's not something you want to have in your graph where it's hard to read there. Also, again, this sort of stepping stone here, this zoomed in image does not necessarily go well with this image right here, because here you're talking about a yearly scale, so each jump kind of represents an increase, obviously. But if you suddenly change how much your jump represents by zooming in on it, again, that's that graphical distortion here again. So it might have been best just to put these as two separate graphs rather than try to have one come out of the other and sort of offer to zoom in the image, because it looks like you're still trying to use this y-axis here, but now your x-axis is much more spaced out compared to what it was over here. So again, trying to be a little bit too creative with it. And it just kind of overall muddles the graph there a little bit. Thankfully, they have these little notations here, which are telling you what the percent increase was. But again, it doesn't really help the overall picture of it there. So again, this might have been better split into two separate graphs rather than trying to kind of fuse them together here. Again, trying to keep it simple is the name of the game here. And then using different or overlapping scales. This is just a weird sort of way to set up the graph, to be honest. You have two y-axes here, one to represent non-smokers, one to represent smokers. Then you have two lines here, one for non-smokers, which is the dot circles, and one for smokers, which is the open circles. You have the age on bottom. It doesn't really talk about what the y-axis actually means here, so it's just a really bad design. Usually you want to, again, keep it simple. Stick to one y-axis, one x-axis, make it very clear on which one means what, and just put your data on that. Again, if you're trying to do too much on one graph, split it up into two separate ones. So most of the time people misuse statistics by trying to do too much on a single display there. Now don't get me wrong, you can do a lot with a single display. There's something called infographics. So infographics are a special type of stats displays which display a lot of information in very creative and artistic ways usually, but they do it in a logically sound and mathematically consistent way where you can actually get the most out of it. And they're very sort of technical to do. And when they're done well, they're great. When they're done poorly like this, they're not so great. So again, in the end, simplicity is key. You're better off doing two good graphs rather than trying to fuse it into one weird graph, essentially. Let me make a mic check here. Okay, it's still on, at least for now. Come on. There you go. Try to go back here. Okay. So what's in a percentage? So percents are probably the most easily misused type of number. We should know that percents are numbers that are out of 100. So if I say 10%, that means 10% out of, or 10 out of 100. So 10 things out of 100 things, like 10 years out of 100 years, 10 candies out of 100 candies, that sort of thing. So 10% means 10 of something out of 100 of something. But people often misuse that or just don't think about it like that. So for example, if I say mathematicians read 10% more this year, whereas biologists read 12% more this year. So as a group, we surveyed thousands of mathematicians, and they read 10% more material this year, whereas we surveyed thousands of biologists, and they read 12% more material this year. So we say biologists read 2 percentage points more than mathematicians. So we say biologists reading rose by 20% more than mathematicians. So did biologists read more than mathematicians? Well, maybe, maybe not. We don't know. Because yes, biologists read 12% compared to the mathematicians 10% more. But what if biologists only start out reading like 10 books last year and mathematicians read 1,000 books last year? So if we have biologists, mathematicians, so if we say last year, biologists read 100, mathematicians read 1,000. This year, if biologists read 12% more, that means they're going to read 112 books. Mathematicians read 10% more, that means they're going to read 1,100 books. Well, mathematicians still read more this year because they started out with a higher base last year. So just because it says biologists read 12% more doesn't mean they read more overall. And again, this is the key pitfall with percentages. People think a higher percentage means a higher value. It's not necessarily the case. When you think percentage, always think of what? That should be your first sort of reaction question there. If people said 10% increase, you should say from what? What was the starting net value? Because that's going to be your perspective. So you really need that base number when talking about percentages. Percentages should always be accompanied by a base value to help you figure it out. Unless you're talking about probability. Probability is kind of its own little special subset, but by and large, when you're dealing with percents, always ask what's the base value, what are we basing this percent on before you infer it further. So these are some basic stats that we're going to be kind of delving into more, but just want to give you a preview of them here. So we have the classic mean, median, mode, which are described here. These are probably stuff you've done before in other math courses. We have the normal curve, which is going to be something that we really spend some time on. So this is a very key part of our course here, figuring out stuff from the normal curve. Variance is kind of like the opposite of mean, median, mode. So mean, median, mode are ways to figure out what's your most typical value in a set of data. Like what's the most typical age for the people on a bus. That's what mean, median, mode are there to help you figure out. What's the most common or typical age for a person on the bus. Variance is to figure out how diverse the ages are of people on a bus. So if you have a very high variance, that means the people on the bus are of a lot of different age groups. So you have some very old and some very young people on the bus. A very low variance means that the people on the bus are all around the same age. Like they're all about teenagers, or they're all about seniors, or they're all about toddlers. I don't know. But variance is a degree of how diverse your population is compared to whatever you're measuring. Standard deviation kind of goes along with variance. Again, another very key concept that we'll get into a lot more later. But standard deviation is kind of like another version of variance. And then range is also another version of variance. Range is just basically the biggest value minus the smallest value. So it's basically how spread out your data is, or how far is it from your oldest person to your youngest person, if you want to think about the age on the bus example. So these two here are different types of variance measures. Like mean, median, mode are measures of central tendencies. Standard deviation and range are different measures of variance tendencies. And then we have our friend the stem plot. So stem plot is a very common statistical tool. If you don't remember how to make a stem plot, I'm going to go over it here quickly. I'm surprised my mic hasn't cut out yet. Let me just double check that again. Okay, it's still going. It's weird. Usually it cuts out by now. So if you remember, a stem plot kind of goes like this. You have your stems over here, and you have your leaf over here. I'm not sure why this line suddenly pops up there. I don't get that. Let me see if I can erase that. No, it erases the E there. It's probably going to come back up when I write it, but oh, there we go. So stem on the left, leaf on the right. Basically what you do is you split your numbers in a very consistent way to help organize them. So for instance here, we have 2-digit numbers. So basically the most common way is to put your tens numbers on the stem plot and your leaf number or your ones place numbers on the leaf plot. So here 21, 23, 24 would be like this. 20, 1, 3, 4. 21, 23, 24, done. So 21, 23, 24. 35, 36, so 35, 6. 45, so 45. 60, 61, so 60 and 61. And then 72, 77. And so this would be your stem and leaf plot. And then usually it's accompanied by a key that tells you how to read it. So the key would be like 8. There's that line again. Don't know why. That's going to be annoying. Let's try that again. 8, 0 equals 80. So it doesn't necessarily have to be a number you wrote down, but a key just basically tells you what the split means. Because if you didn't put this on there, they might think that, this means 7.2. Or maybe this means 727. We don't know. So the key is important so you know kind of how to read your stem plot. That way you know it's AD, not 8.0, that sort of thing. And that's the end. So this is just kind of the last little thing to show you the stem plot. But that's kind of the overall lesson for the chapter 0 there, just a kind of a basic overview, introduction, and kind of things to avoid and what to not do essentially. So again, make sure that you kind of have an overall idea about the basic concepts here. Mean, median, and mode you should be somewhat familiar with already. We'll go over them again in detail, but these are what's coming up down the pike here. So these concepts here are what we're going to be first delving into and expanding on greatly. And again, the normal curve, we're going to be hearing that a lot, especially second semester and late first semester, about kind of getting into what a normal curve means and how to work with it there. So that's it for this video. Hopefully it helped you out. Have a good day.